All right, in this video we're going to talk a little bit about curved motion. So this is general motion along a trajectory. So for example, you have an object that's moving along this path, and at different points in time you're considering what the change in momentum is and what the forces are that are acting on that object. So going back to our derivative form of the momentum principle, we know that the momentum change of that object is equal to the net force that acts on that object. We can use a description for the momentum vector, which allows us to determine how each of these components of the force in the direction of motion and perpendicular to it are changing. And I'll show you how that works right now. So we're going to take the derivative of the momentum vector, which is the magnitude of the momentum vector times the unit vector. We're going to use the chain rule. We're going to take the derivative of the first part times the second part. And then we'll take the first part times the derivative of the second part. So that, through the chain rule, is the derivative of the magnitude of the momentum vector times p hat plus the momentum vector magnitude times dp hat dt. So you can already sort of see what I'm going after here. This first part is in the direction of the momentum vector. So that means if we're looking at an object that's moving through a trajectory and it has some momentum that is changing, there is a component of the rate of change of momentum which is in the direction or opposite the direction of that momentum vector. This part right here is related to a parallel component of the net force. By parallel, I mean parallel to the momentum vector. So as this object is moving through this curve here, perhaps it's speeding up, and there's a net force that points like this. That'd be this net force. And there's a component of that net force which is parallel to the momentum vector. This other part is tracking how the momentum vector changes. It's tracking the directional change. And so this part right here is always perpendicular to the momentum vector. That's the component that we haven't decomposed here. That's this part right here. That's the perpendicular part. So there's a part here of the momentum change and the net force component that worry about how fast the object is going, that is how much it is speeding up or slowing down. And there's a component of the momentum vector change, or the perpendicular component of the force, which tracks how it is turning or changing direction. And so at each point along this trajectory, we can decompose the net force. For example, in this case, let's say that the net force is pointing in that direction. So in that case, there's a component of the momentum vector which points opposite the momentum. And so this object is slowing down, but it's turning as well. This perpendicular component always points inward towards the turn because an object is turning inward, so it's experiencing a net force inward. These two you might have seen in the past in different ways. This component, the parallel component, is often thought of as the mass times the tangential acceleration. It's tangent because it's tangent to the trajectory. And this component is often thought of as the mass times the centripetal acceleration, the acceleration which points inward towards the curve. This centripetal acceleration is often written as v squared over r, and we'll assign a normal unit vector to that component. That normal unit vector always points inward towards the curve. So in any sort of generalized motion, you can decompose the forces along a direction parallel to the momentum and a direction perpendicular to the momentum. And these are connected directly to this tangential and centripetal acceleration.